computer. It is a great pleasure to introduce Minh-Tâm Trinh, who will be speaking about the one-point uniformization of BunG.
So I think you need to let me share my screen.
Ah, that is a very good point. Advanced sharing options. All participants can now share. Sorry, we should have thought of that.
Great.
Brilliant.
So, okay, can everyone see the screen?
Yes, it looks good.
Great. Okay, well, thank you very much to Aaron and Nikolai for inviting me to speak. So I'm supposed to cover two big theorems today, the Beauville-Laszlo gluing theorem and the Drinfeld-Simpson reduction theorem. So on the very first slide, I just list out all the references which helped me to write up these slides. I found this actually, in the case of the Drinfeld-Simpson theorem, it's very gory, and I'm not going to give all the details, and I'm just going to sketch the big ideas, and hopefully the parts I leave out will not be too large of gaps. So what's the setting? Throughout this talk, we're working over an algebraically closed field K. G and X and BunG are the usual notation. And the whole story begins with this very famous observation of VIII, which I think came up first in Julian's talk, which is that you can write the moduli space of principal G bundles over X, or G torsors over X, as a double quotient space, a double coset space where you start with G over the adeles of X, you quotient on the right by G of the integral adeles, the ones for which at every place of X, your coefficients live inside of the ring of integers of the local field. And on the left by G of f sub X, the function field of X, which is to say, you can think of as the field of functions at the generic points. For the case of K being the algebraic closure of a finite field, well, then all of these things are endowed with some kind of non-Archimedean topology. And in particular, if you take G simply connected semisimple, and you pick any points on X, then the strong approximation theorem from number theory in its function field version says that the setwise products of G of f sub X with G of the local field at V, the chosen points, is a dense subset in this non-Archimedean topology inside of G of the adeles of X. So here, of course, we embed f sub X, the function field, into the adeles via the diagonal embedding, and we embed the local field at V into the adeles simply by taking the components of the adeles at V. And so a nice little exercise is to show that from strong approximation, you can infer that the obvious map from G of the local field at V modulo G of the ring of integers at V into the K points of the moduli space of bundles is surjective. And here, again, BunK we're just interpreting as a double coset space. So we'd like to geometrize the statement. And by geometrize, I mean promote it from a statement about sets of points to a statement about spaces. And by spaces, we mean schemes or stacks. And as is traditional in algebraic geometry, when we mean to promote something to the level of spaces, it means that we not only want to show the statement at the level of K points, where K is the base field, but we want to show the statement for R points as R runs over all possible K algebras. And in this setting, surjectivity must be understood in an appropriate sense. So if you have a map of two spaces, two stacks over K, you don't necessarily want the bare map on R points to be surjective, but maybe surjective after you replace R with R prime, such that the map from spec R prime to spec R is some, italic cover. And so we call that ital surjectivity. The geometric incarnation of this one-sided coset space, G of F sub V mod G of O sub V, is of course the affine Grassmannian, which I think Professor Ngo discussed last time. I wasn't able to come to the talk, unfortunately, but that's what it says on the agenda. So the geometrization of this surjectivity is the statement that for G, a simply connected semisimple algebraic group over K, there is some ital surjective map from the this affine Grassmannian into BunG. And here, note that I write the affine Grassmannian with a subscript little v, because throughout this talk, I want to identify the abstract field of formal Laurent series, or the abstract ring of formal power series, with the concrete field of germs of functions at V, or the ring of integers thereof. So meromorphic functions, formal meromorphic series at V, or formal holomorphic series at V, if you want to think of it in the complex number language. And moreover, this map is not only surjective, but in some precise sense, it is also smooth. And so you should think of this as a submersion in the language of differential geometry. And in particular, this is why it's called a uniformization map. It's a uniformization because it replaces this mysterious thing BunG with something that we pretend we understand very well, namely some infinite dimensional homogeneous space. So the proof has two steps. The first step is the Beauville-Laszlo step, and it's saying that this local affine Grassmannian is exactly the same as some global analog, where instead of using local data near V, we use global data along the entire curve X. And the second step is the so-called Drinfeld-Simpson theorem, where we'll show that the map from this global affine Grassmannian to BunG is ital surjective. So we need a bunch of notation, and unfortunately, the notation can be slightly misleading. So I just want to clarify what's going on. So throughout R is some K algebra. We write delta sub V comma R for the spectrum of the completed tensor products of R with O sub V. So of course, what this completed tensor product means is, like, you should think of this as R formal power series T, where T is some sort of uniformizer or local coordinate at V. And similarly, we write delta cross sub V comma R for the same thing, except not only do we allow power series in this local coordinate, but we also adjoin polynomials in 1 over T. So this notation is not analogous to the notation below. So not only do we need these deltas, but we need these x sub R and x cross sub R. So x sub R is just the product over spec C of x and spec R. And xr cross is the same thing, but for the punctured curve where you take out the point V. So the top things are completed tensor products, and the bottom things are just usual tensor products. So the point of introducing this notation is that now we can rewrite the affine Grassmannian in a way which I think has been discussed in this language of bundles. So a priori, the affine Grassmannian is this sheaf quotient of this sort of loop group by this arc group. But you can rewrite it as the space of pairs consisting of E and alpha, where E is some G torsor over your disk delta, and alpha is a section of that torsor over the punctured disk. And to make this definition work in general, we use these completed tensor products. So deltas of V comma R and delta cross of V comma R. So on the level of K points, there's basically only one torsor you can take, but you can vary this section alpha. And so on the level of K points, the only thing you're really able to change corresponds to changing some coset of the arc group. So the global affine Grassmannian is defined in the analogous way, but with this global curve X sub R and this punctured global curve X sub R cross. Any questions so far?
Yeah, just in the statement of the theorem, by in smooth, you mean it's actually like a filtered unit of smooth varieties, the fibers?
Yeah, so maybe one should be careful about the transition maps, but yeah, I won't actually discuss the proof of that. I'll discuss the formal smoothness. So I'll just prove that I'll prove lifting along square zero extensions at the end. And it's very easy.
I see, because like in smooth a priori is definitely stronger than formal smoothness, right? So I just
yes. Yeah, I'm not going to talk about all the finiteness stuff, that finiteness conditions and so forth.
Yeah.
Yeah. But thanks. Good question. Any other questions? So certainly there's a map from this global affine Grassmannian to this bundle theoretic presentation of the usual affine Grassmannian, which is where you just restrict the torsor from the whole curve to the disk, and you restrict the section from the punctured curve to the punctured disk. At the same time, there is also a map from the global affine Grassmannian to the moduli space of bundles, because you can just forget this section alpha on the punctured curve. That leaves you with a G torsor over the whole curve. So now let's discuss this Beauville-Laszlo step. So we want to show that the forgetful map from the global affine Grassmannian to the local one is an isomorphism. So at the level of just informal language, this is an extremely obvious statement because we have all these intuitions from complex geometry. And the problem is that we really shouldn't trust those intuitions. Why shouldn't we trust them? Well, because formal power series are actually extremely different from power series which converge in some disk in the complex plane. They're extremely different things. It's a bit off topic, but I think a really nice example of how things can go terribly wrong if you try to treat them interchangeably is a phenomenon by the name of Borel resummation. But I digress. So so you'd like to say that if you have a point of the local affine Grassmannian corresponding to a torsor over the disk and its section over the punctured disk, you can use the punctured section to glue your torsor to the trivial torsor over the punctured curve. So, you know, your picture is pretty obvious. You've got this punctured curve, punctured curve that looks like this, and you've got your disk like this. And morally, you want to say that this alpha is a transition map on their intersection, which is delta cross. And in highbrow language, that means doing descent along this map. But there are some problems with this intuition. So firstly, descent is really only something you can do with flat maps. Why is flatness so important? Flatness is kind of the essential algebraic ingredient in gluing in the language of, in the world of schemes and stacks. So if your ring R, your test ring R is not Noetherian, then it's possible to build up examples where this map is not flat. And I don't even remember what these rings are, but they exist, and I've listed the stacks project tag for them. And there's an even more basic question, a more basic problem, which I suppose was overlooked for a long time, but which I learned about from a paper of Heinloth. So even if you restrict an Noetherian R, how actually do you glue these things together? So a descent datum is a very specific thing. It's a kind of, it's to give an isomorphism between the restriction of one bundle and the restriction of the other over some open set where they intersect. Except here, we don't really have an open set. We have delta cross sub v comma r. And it's just not clear how to use alpha to produce this isomorphism. We actually have to do some work. So Heinloth observes this and wrote it up. So let me talk about his solution first, because actually I find it a bit simpler than Beauville Laszlo. So first, the whole Noetherian thing, non-Noetherian thing, it's actually very easy to deal with. The point is that both the local and the global affine Grassmannian are filtered up by actual finite type schemes. So of course, they themselves are in schemes, but you can filter them by things which are basically Grassmannians under closed embeddings. And so what this means is that the functors of points that they represent are completely determined by what they do on Noetherian K-algebras. So one can restrict this whole question of descent to studying test rings R, which are Noetherian. So, let's dispense with this whole non-Noetherian issue. So going to the second problem, we can actually, write out in gory detail what it means to give a descent datum for two G torsors, one over the disk delta sub v comma r, and one over the punctured curve x sub r cross. And the point is that you're going to end up looking at a bunch of possible intersections. You look at the intersection of, x cross with itself. You look at the intersection of delta cross with, the intersection of x cross with itself, the intersection of x cross with delta, the intersection of delta with x cross, which is the same thing. And finally, the intersection of delta with itself. The last one is the tricky bit, because you're not really taking a intersection in the sense of set theory. You're taking the fiber products in things mapping down to x. Everything here is a map down to x, right? And you really want to take the fiber products of delta over its x with itself. And not only over x, but everything is, kind of base changed up to r. And all of this has to satisfy some co-cycle condition. So the trick which makes everything run is that, in fact, this thing can be rewritten as a push out in the category theory theoretical sense. So there's some diagram. I guess I can draw it here. And again, I'll suppress all the subscript r's. So how shall we write this? Something like this. You've got your fiber project down here. What we're claiming is that the fiber product of delta with itself over X is the bottom right corner of a push-out diagram, where you push out the unpunctured disk along the map, the diagonal map, from the punctured disk into the fiber products of the punctured disk with itself over X. That was a mouthful. But the point is that now, if you're given only the data of the section alpha, which is some section of E over delta cross, then that basically corresponds to some elements of G of delta cross. And I'll stare at this G inverse box times G. So this is the notation for pull back G inverse and G to G of delta cross fiber products over X with delta cross. Because you have this thing on here, so that's down in this part of the diagram. And at the same time, since its restriction to the diagonal is just the element 1, which certainly extends to a section on all of the delta, you can fill in the rest of this push out. And therefore, you see that this box times extends to a section of G over delta fiber products with itself over X. So this is an explanation in pure symbols of what is really going on under the hood when you kind of build this descent datum from your original section A or alpha over the punctured disk. So I say that high-law solution is simpler, but in speaking through it, I realize it's actually very complicated. In some sense, Beauville Laszlo, it's much more tricky, but it is much easier to state because it is really a statement about just commutative algebra. So
sorry, can I just make a quick comment about the Heinloth thing? Because I was very confused about this at one point in my life. That like what's really weird here is that like you were saying, your intuition from analytic geometry or whatever would be that like the intersection of the disk with itself would be the disk because you expect it to be open or whatever. And in fact, if we were using really the formal spectrum of power series, that would be true.
That's
but because we're using the actual spectrum of power series with its discrete topology, what this delta cross delta over X is really it looks like spec of power series, tensor power series over polynomials, which is some complete garbage. So that's like kind of what you're fighting against here.
That's right. And in fact, maybe that's a good thing to point out. We can write out this in commutative algebra if we really want to. I shouldn't denigrate Heinloth. I think this is a very interesting point. So what Justin is saying is some statement like this geometric object is the spectrum of this horrible ring. And these two copies of the coordinate T must be different. But I'm going to use notation. Certainly that is very different from the power series ring itself. Yeah, so that's a really great point. Somehow the Laszlo solution totally sidesteps all of this. They just do everything directly. They produce the datum directly, and part of the cost of doing that in a way that's easy to understand is that they restrict to the linear case. So you may want to rewrite everything in Heinloth's solution in this linear language. Maybe that would be an interesting exercise. But if we're working with linear things, we may as well work with modules. And in fact, the statement holds for arbitrary modules. We don't even assume coherent module, I think. We should think of these now as vector bundles, right? We have an M prime and an M double prime. M prime is a module over A localized at the inverse of some coordinate t. So you should think of M prime as the thing that lives over the punctured curve. And then double prime lives at A completed at t. So you should think of M prime, M double prime as something living over this infinitesimal disk. And suppose we're given some sort of gluing between these things. So this is really in disguise. This is the alpha from before, and it becomes the descent datum for gluing M prime to M double prime. In our setting, we're working with t, the local coordinate at the points on the curve. So certainly multiplying. Yeah. Hi.
When you write A is what is the A versus R is my quick confusion here. Is A just an R algebra or sorry?
No. So you should right. Maybe I should go back up here. So you can see this quadrangle I've circled.
Oh, I see. That's where, yeah, that's the algebra map. Okay.
Yeah. So when I write step A, I guess I'm saying pretend, without loss of generality, we can even work with affine curves, and then take spec A to be the coordinate ring over K of a curve over K. And so spec A plays the role of X. And in fact, you can even have it play the role of X sub R. So here, I guess if you want to be really explicit about it, I'm thinking of A as R join T. Okay?
Fantastic. Thanks so much.
Yeah, no problem. So the point is that T, when you multiply R join T by T, it doesn't kill anything. That's the only assumption on these modules that Beauville and Laszlo use. So what they do is much more general than even talking about curves or talking about rings of this particular form. It's for a very, very general ring A, and all you need is some elements T inside of A, such that when you multiply M double prime by T, you don't kill anything. And everything stays intact. Okay. So the claim is that you can find some module for the ring A itself, which we'll call N, such that base changing N to the localization A adjoin 1 over T recovers your M prime, which is your thing over the punctured spec A, and localizing, base changing N to the completion of A at T gives you M double prime, which is your thing over the completion of spec A at the point where T equals 0. So this is very, very, very slick and also kind of crazy. There's really only one thing that N can be. And unfortunately, when you write it out in commutative algebra, it's not completely clear why this works. But then in the course of doing the proof, you find out, this has to be the only thing that can work. So you take N to be the kernel of this composition. So here I'm not writing an exact sequence, I'm just writing the composition of a bunch of module maps. So first, we claim that this whole composition of maps is a surjective map. How can you check that? Well, it's enough to check that it's surjective when you tensor everything with the localization, and it's also surjective when you tensor everything with the completion. So this is a nice little exercise. The idea is basically that even though the disjoint union of spec of the localization with spec of the completion, even though this is not a flat covering of spec of A, it at least surjects onto spec of A. And so that's why you can test surjectivity of module maps by pulling back to that non-flat covering. Anyway, so let's assume we've proven this is surjective. Well, n is the kernel, so now we do have an exact sequence, right? It looks like this. And now let's look at what happens when we tensor this exact sequence with the various other rings. So if you tensor it up to the localization, what's going to happen? Well, this first term is going to give you n just tensor with A localized at t. And this thing, so how does this go again? How does this go again? What I want to say is basically that when you tensor the last term up to the localization, that part dies. Although I'm actually getting a bit confused because this thing, right, if you literally just tensor this up to the localization, you don't get back itself. You get back m prime tensor over A with the localization of A. But the point is we're trying to say that if we tensor up, we get back the isomorphism between the localization of n and m prime. Let's see. Well, maybe it'll come to me. This is how it should go, though. The part I thought was to be much harder is that you want to do the same thing on the completion side. So you want to say if you tensor this exact sequence with a hat, right, you get back this map. And the whole point is going to be that it's not clear that the tail end of your exact sequence stays surjective when you do that, because this map is not flat. But the completion map from A into A hat is not flat. However, you have this crazy trick, which is that you have this weird module, and you had assumed that n double prime has no t torsion. And so if you want this tail end to stay surjective upon tensoring to A hat, you're checking some Tor vanishes. Well, okay, but note what you're taking Tor of. One of the terms involves this crazy localization of m double prime. And if you think about what this actually means, well, it's clearly filtered according to the pole order of t, right? So you've got some in limit, and you can pull out that in limit. That definitely commutes with taking the Tor. So you're left with computing Tor of this thing. But you know that multiplying by t to the n is injective because m double prime has no t torsion. And so the upshot of this is that I think the point is you can basically treat this as a free module. And the point is that this Tor1 vanishes. Okay. So that's
sorry, Tom. I think
yeah.
the comment that you said about that third term dying when you tensor up to A1 over T is in fact clear because it introduces a 1 over T on the bottom and the top. M prime prime, right?
But I'm worried about the middle. I'm worried about the middle term.
M prime is already a module over A 1 over t. So when you sort of tensor it by a1 over t, it does nothing, right? I mean, t is already invertible, so it should just be back m prime, right? M prime is already a modulo over a1 over t.
But I'm confused because, for example, what if m prime is like a over? What if m prime is this for itself? You know, if it's equal to the localization, this is certainly not. I see what you're saying. You know, that's the point. So even this, I think this is actually isomorphic to a adjoin 1 over t.
I think so. Yeah, I would need to think. I see why I gave you pause, but yes, I think that is correct, right?
Yeah, thank you. Okay,
Yeah.
that resolves my confusion. Yeah, this is another tricky point. Yeah, so you're taking a tensor product with a localization, which is like restricting to an open subset. So you're completely right. It shouldn't add another factor of the localization. That should just be absorbed because you can always multiply either side by positive powers of t. So you can always move like a pole from one side to the other. And that is why you get this.
Yeah, 10 out of 10.
Yeah, sorry, I really concentrated on the other side of the theorem, but yeah. This is the key part. This is the key part. There must be some other applications of this trick elsewhere in algebra, but I don't know what they are. Okay. So let's go on to the Drinfeld-Simpson theorem. This is where I want to spend most of my time. So now we have this global affine Grassmannian. We want to show that its forgetful map to BunG is a tall surjective. And we do this in 2 steps. So first we show that any G torsor over X sub R, which we think about as a family of G torsors on X parameterized by spec R, admits a reduction of structure group to B once you perhaps replace R with another ring R prime, such that spec R prime to spec R is a tall cover. So recall what a B reduction is. It means that you can find some B torsor, F, such that you obtain your original G torsor from F by changing the structure group using this so-called associated bundle construction. So form the product of F and G and quotient by the diagonal action of B, given by this formula. The first theorem of Drinfeld and Simpson is that this B reduction exists. And the second applies this theorem to prove that if you fix a base point of X sub R, I should really say a R points V of X, and you restrict your G torsor to the complement of that base point, then up to changing R to R prime, you can ensure that your bundle literally trivializes, not just locally, but literally does on X. So the only tau cover you're taking is with respect to R, not on XR itself. And this proves that the map from GR globe to BunG is tau surjective because it's saying that in families of G torsors, after you puncture your curve, you can trivialize that family of G torsors uniformly. And that is like reconstructing this section, which is the data you forgot in passing from GR globe to BunG. So that proves the surjectivity of tau locally. So throughout this proof, we are using this crazy explicit way to describe the B reduction. So if you have a section of the flag variety bundle So a bundle whose fibers are copies of the flag variety of G, that you obtain from E just by quotienting by B, then you can reconstruct a B reduction of E simply by pulling back the structure map from E down to E mod B. So is this E mod B thing clear? I'm just saying G acts fiber-wise on E over X, therefore B acts fiber-wise on E over X, and the quotient E mod B is some fiber bundle whose fibers are copies of the flag variety. Okay, so I restate what we're trying to do first. We're trying to exhibit a B reduction of any G torso E over X sub R. So first, there is a actual space that parameterizes sections of the bundle E mod B, and these of course correspond to B reductions V. So we want to show that at tau locally on spec R, we can trivialize the space of sections. Does that kind of make sense? So it's a bit weird because this stack of sections depends on R and on E. So R is fixed and E is this torsor over X sub R. Once you fix those, then you form the space of sections, and it is now, what is its input? Well, this is a thing that lives over spec R, and you have to evaluate it on R algebras R prime. Okay. In order to trivialize something in tau locally, it's enough to show that the smooth locus, so the locus of points where this map is smooth, surjects onto the base, because smoothness means that you have local lifting, right? So we want to show that the restriction of the structure map from S sub R comma E down to spec R to the smooth locus is a surjective map. This itself we do in 2 steps. So first, we just show the original map as surjective on the level of K points. And then we have the crazy step, which is we basically what we're going to do is once we know it's surjective on K points, and we pick a K point X of spec R, well, you can think about that diagrammatically as you got spec K going to spec R going to X. And you've got a bundle over X cos spec R. So over here you have X R, and over it you have E. And you can pull everything back to spec K. So when we pull back XR to spec K, we just get a copy of X again. Now, we know that P is surjective on K points, so we can at least find some Y, right? Some Y in this stack of sections, which lifts our base point X. And what you want to do is you want to modify that Y so that it belongs to the smooth locus of the map P. But it's hard to do that directly. And so it involves this detour into this insane cohomological calculation, which once you unpack it, it's actually not so insane at all. It's actually becomes something very standard. But the trick is to see where these crazy formulas down here are coming from. So I won't explain what these formulas mean now, but I will do that once we get to that step. Let's start with the easy step.
So Minh-Tâm, comment.
Yeah.
We usually around this time take a break, so if you feel
Yeah.
convenient place for a 5 to 10 minute breather, let us know.
Yeah, how about we can stop here if you want. I could also just cover the next slide.
Okay, is now a convenient breakpoint for people? Well, I guess that they probably won't be able to answer, but is that a convenient breakpoint for you, Minh-Tâm?
I didn't do anything. I am sitting at home.
Okay, brilliant. All right, so let's take 10.
Resume at 5.
Actually, yeah. So yeah, let's re-meet at 5 p.m. Central Time. So that's 8 minutes from now. Brilliant. Thanks so much, Minh-Tâm. This is wonderful. So we'll see everyone in 8 minutes, and I'll pause the recording. Oh, and feel free to ask any questions if people have questions as well. It's another thing to be done here. Right.
Well, to quote Benedict from 2017 at MSRI, once more into the breach. So where were we? Yes, we were trying to prove theorem A. We had divided it into 2 steps. I said there was an easy step and there was a gnarly, nasty step. Let's do the easy step. We want to show that a certain map is surjective on K points. That map, and more precisely, is the map from this space of sections of the associated bundle of some G torsor E with fiber to Flag variety, which has a map down to spec R. So if you unpack what it means for this to be surjective on K points, well, as I was trying to draw sloppily on the Zoom screen before, checking what this is when you plug in K for R prime basically boils down to checking what this looks like in the case where you take R prime to be K. So then this X sub R prime simplifies to X, basically. And you can treat this E as a G torsor over X itself, not over X sub R. And I don't know why that keeps happening. You just want to show that this flag variety bundle, E mod B, has a section. This is just by the evaluative criterion of properness. So start with a G torsor over X. You can trivialize it at the generic point of X. This is not completely obvious. It requires G to be connected and reductive, but you can do it. Since you can generically trivialize it, you can trivialize it over a dense open subset of X. So then pick a section of that flag variety bundle over the open subset. Well, you know that the flag variety is proper. So you can always fill in the limit points of this section over the punctures in your open subset U. And therefore, the section extends to a section of the flag variety bundle over X itself. So there are lots of generalizations of this. The key idea is Steinberg's theorem. And I just want to remark that there is a proof of Steinberg's theorem, which is kind of in the spirit of Ngo-Bao-Cho type math, but really goes back to Rondinaghi and Denis Gatescory. So using the regular centralizer scheme over G frac mod G, there's a way to prove Steinberg's trivialization theorem, where you basically reduce the structure group down to this regular centralizer. And that's in Gatescory's notes from his 2009 seminar. Okay, so then there's this nasty part of the thing we're trying to prove. So I have to restate what the goal is because it's so complicated. Suppose you have an R. Suppose you have an R point of BunG. So it's a G torsor E over X sub R. Suppose you have X, which is a K point of spec R. And suppose that you have a point Y, which is a lift of X to the stack of sections S sub R comma E. By definition, what Y literally is is a global section over X of the pullback along X, little x, of E mod B. So that's another mouthful, but this is the key point. Okay. So whatever this thing is, where's my annotate marker? X star E lives over big X. And similarly, X star E mod B is some flag variety bundle over big X. We would like to modify this lift little y in such a way that it lands in the smooth locus of this stack of sections S. And the way that you detect the smooth locus is using deformation theory. Deformation theory is basically a cohomological theory, a cohomological obstruction. So form the relative tangent bundle of this fiber bundle, that's going to be some vector bundle on the total space. The point is that, okay, now we can pull back that vector bundle down to big X using our given section S sub little y. And H1 of the resulting vector bundle on X by abstract nonsense is something that controls how much you can uniformly deform S sub y. So more precisely, little y belongs to the smooth locus of the space of sections. That is to say, somehow you can kind of perturb it in every possible direction. There's no obstructions to how you perturb it, precisely when this H1 vanishes. And notice something very magical happens in the course of all this nonsense, which is that we started with something that lived over X times spec R, right? And we did all these things which depended on R, but ultimately the problem we're trying to solve doesn't involve R at all. This statement doesn't involve R at all. We just want to find, given a fixed little x, which you can now think of as a k point of big X, we want to find a lift of it to some y such that this holds. And now we can just think of this little y as some section of this bundle, which doesn't depend on R either. So long story short, you can forget everything in the top half of this slide. The point is this: you can forget R. We have reduced the problem to studying H1 of some vector bundle over X alone. So now I'm going to lighten my notation because I don't want to carry around all this stuff that originally depended on R. Let E white circle be the trivial G bundle over X, and let E black circle be the pullback of our given G torsor over XR to X along this map little x. So I'll just call them like, let's call them E ping pong and E bullet. Is that okay? E bullet is the thing we were working with over here. E bullet is our X star E from the previous slide. The point is that working with E bullet is hard. So the rest of this proof is going to be gradually as massaging it into E ping pong. Question?
May I ask, for the definition of the section SY, do you want to pull back along Y, not X?
Do I want to pull back along?
Yeah, so you put X star E.
Yeah.
But doesn't that then give you like a bundle over little k?
So E lives over X times spec R. So maybe I can draw the diagram again to make it clear. So we started with X lower subscript R, which is x times spec R. We have an E over it. So I mean, what I'm doing is this. Does this make sense?
Yeah.
Sorry. Sorry, I'm confused about that. I see. So this is truly about over x by pulling back.
Yeah.
Sorry.
No. So I appreciate this very much because these slides are very badly written, partly because I wrote most of them last night. But we will plow on.
Fantastic.
No. I think actually Lurie's notation may have been clearer, but I was very confused by Lurie as well. I didn't think there's any good write-up of this. Drinfeld Simpson, by the way, will not give you most of these details. I found Lurie's account to be probably the clearest. And I was just trying to massage his notation into something that I could use here. Anyway, this is the important diagram. Okay. So now we can forget, little y, we can forget little x, all this stuff. What really just matters is that suppose we have a section, little s, of E bullet mod B, right, this flag variety bundle over x. We know that one such section exists because of what we did in the first step. We showed that for this flag variety bundle, sections always exist at the level of just the bundle over x itself, right? So the k-point problem. So notice that this section of E bullet mod B corresponds to some B reduction of E bullet, right? And that B reduction is some B torso over X, so it's generically trivial. So you can find a section of it over some dense open. And if you think about what that means, you can think of the trivial B bundle as corresponding to like E ping pong mod B, and this section of that, right? The zero section, in fact, or the section which takes the identity coset of G mod B. So the point is that just using some generic triviality argument, you can arrange an isomorphism between the B quotients of the trivial G bundle E ping pong and the B quotients of your given G torsor E bullet over some dense open U. And moreover, you can arrange things so that your given section, little s, is obtained at least over U from the identity or zero section of this trivial bundle by composition along this comparison isomorphism beta. So that's what this is saying. So in what follows, let's let capital D be the effective divisor obtained by removing this dense open U. Actually, I think I have to be careful. I think you can't always just take D to be this. I have the feeling that you may want to allow D to have doubled or multiple points with multiplicity. So the right statement should be something like the support of D is a subset of the complement of U. Is that okay? But I think that part of this lemma down here is going to be the assertion that some D which makes all the statements work exists. So these slides have to be modified.
Minh-Tâm.
Yeah.
Is this because this D divisor actually changes? So secretly still like worrying about like the base being R and the D can change, like, right? Can kind of deform into like multiple points, deform into like extra multiple points, right?
Yeah. So I guess, Griffin, what you're saying is that if we step back into the larger picture, we're trying to extend some trivialization on one G-torsor to a whole family of G-torsors, right? Over spec R. And the issue is that we can't really do it directly. We have to modify this trivial bundle somehow. And the way we're going to do that is by blowing it up again and again. But we may need to blow it up over the same locus several times. So I just think maybe to be safe, I should allow D to be non-reduced. That's the highbrow or the big picture explanation for why I'm being cautious. So part of this lemma should be there exists a divisor D such that the support of D is in the complements of U. And an M, some space, such that M is equipped with these two maps and satisfies a bunch of other properties below. I don't know if I answered your question, Griffin, but is that okay?
Yeah.
I don't really understand this very well, but I'll try to explain what part of algebraic geometry inspired them. So they will exhibit for you, Drinfeld and Simpson will exhibit for you this M and this D, such that the following things happen. First, M is equipped with maps down to E ping pong mod B and E bullet mod B. So it's like a correspondence between them. Literally, M is going to be some kind of blow up of E ping pong mod B. And in particular, away from this divisor, it's going to be an isomorphism onto E ping pong mod B. And one consequence of this is that if you have a section of E ping pong mod B over X, which agrees with this identity section over the divisor D, then you can lift it up to M uniquely. So that's what the second item in this list of statements is saying. And from that, I think you can further prove that, the point is that the description of M as a blowup over points involving the divisor D shows that the tangent bundle of M relative to X is the pullback of the tangent bundle of E ping pong mod B relative to X, twisted by T. And at the same time, so all of the statements 1 to 3 involve this map. At the same time, M has this other map down to E bullet mod B, and we require that it is compatible with this trivialization. So this beta tilde is a lift of beta. And in fact, beta factors through beta tilde when you restrict beta tilde to the parts of M that lives over U in X. So the name for this kind of construction is, I guess, coming from birational geometry. M is called the dilatation of E ping pong mod B along the data of the identity section and the divisor D. This is not a typo. I don't know if you any of you have seen this before, but the word dilatation is different from the word dilation. Dilatation is a medical term in particular. So the definition is inductive. The base case is when your divisor is empty. There you're not blowing anything up. And in general, if you know what it looks like for a divisor of a given length, and you throw in one more point, what are you going to do? Well, lift your given section of your original space up to the total space of what you already have, and blow up your total space at the point you just threw in, which you identify with the point of the total space via this lifted section. That's what this complicated notation is trying to say. And then, sorry?
Oh, wow. Okay, that's interesting.
Catherine, were you going to say something or? Maybe radio static.
I think
So-
you got, oh wow, from the audience, which is an admirer.
I don't deserve to be admired. I am merely the servant of Volodya and dear Carlos.
We all,
Anyway, the point is take this blow up and then subtract off the fiber of your total space, which lives over your original point P. I don't know how someone comes up with this, except maybe from doing birational algebraic geometry for a long time. I guess maybe it's a standard thing. But the key point of this construction is that is this lifting property, I guess. Not only is it a blow up, so it's an isomorphism over some dense open away from the divisor where you're taking all the blow ups, but moreover, you started with some section of some bundle, and now you're blowing up the bundle, and you're trying to make sure that you can lift that section up to the blown up space in a controlled way. So the point also is that this dilatation is equipped with some universal property. And I think the universal property is basically, if you have a section of your bundle, in this case, E ping pong mod B over U, then, and you know how to transfer that to a section of E bullet mod B over U, then there must be a induced map from M down to E bullet mod B. That's some kind of universal property that makes M initial among, I guess, all possible weaker dilatations. And that's where this map beta tilde is coming from. Okay, so the point of all of this is that now we can basically replace our E bullet with our E ping pong. So by a bunch of comparisons along the two legs of this correspondence, which are given here, you see that you can trade in the relative tangent bundle you were studying for a relative tangent bundle of this trivial bundle instead, twisted by some divisor. So the point is that we started with some arbitrary little s, and I'm saying that after you possibly replace your s with some s tilde, another section of E bullet mod B, then you can pass up and through this correspondence and compare the cohomology group you were studying with the cohomology group involving E ping pong mod B instead. So what we're trading is we're trading S for S tilde. S tilde is defined in terms of some composition. And that means that we can trade the pullback of some relative tangent bundle along S for the pullback along this new section. And in turn, we can replace this blue thing with this red thing. So the pullback of the relative tangent bundle of E ping pong mod B over X, pulled back along a particular section sigma, twisted by the divisor D. And now we just want to show this red thing as H1 vanishing. this turns out to be almost the end of the proof, because now we're working with the trivial bundle. E ping pong is a trivial bundle. So the section that we want to choose is equivalent to just a map from X into the flag variety, right? Since this is this E ping pong mod B is essentially X times the flag variety as a total space. So this is a devisage down to the case of the projective line. I guess the key point to mention here is that one of the things you need to do is to reduce from this tangent bundle of the flag variety itself to something a bit simpler. And the way you do this is you notice that you can filter the tangent bundle of the flag variety by these canonical line bundles associated with co-characters of the maximal torus of the Borel. So pick a maximal torus inside the Borel. This is we'll call it T, and we know what Picard group of the class length stack of B is. It's the same as the Picard group of the class length stack of T, which is just characters of T. So by pullback, any character of T gives rise to something in the Picard group of G mod B, which is just line bundles on G mod B. And so if you have a map from X into G mod B, you can further get something in pic X, and you can take its degree. So any map from X into G mod B can be identified, well, gives rise to a linear functional on the co-character lattice, on the character lattice, and that is the same as a co-character. So altogether, you can reduce from this tangent bundle down to these line bundles attached to co-characters. And then there are a few more steps, but you reduce to looking at the so-called anti-dominant co-characters. And after you take a covering map from X down to P1, you can reduce to the case where X is P1. And then you're proving some statement, which you can check literally by hand, because P1 has some nice coordinates, and everything becomes completely explicitly computable. So this becomes some just some Lie theoretic statement, some group theory statement. And I think for SL2, it's just saying that there are rational maps from P1 to itself of positive degree, which is certainly true. And the general case is kind of like that. That was theorem A. So the last theorem in this talk is the idea that having shown that any G torsor over X sub R admits a B reduction, it's hollow locally on spec R. Let's use this fact to show that if, in addition, G is simply connected and semisimple, then a tau locally on spec R, we can trivialize E after puncturing X sub R in a section of its mapped down to spec R. So how does this go? So the first trick I'm actually quite shaky about, because there are all these things which I guess experts know very well, but which I find a bit scary to prove in the setting of X sub R. If it were just a curve X, I wouldn't be so scared, but I'm not actually sure. I haven't gone through the whole details in the general case. So a B reduction exists, right? You can fix a B reduction F of E. And the next thing you want to do is you want to say, actually, we can go further. We can get a T reduction. So to do this, you use this kind of stupid fact that T is both a quotient of B by some unipotent radical, right? And at the same time, it's a subgroup of B, because B is the semi-direct product of T with a unipotent radical. You'd like to replace F with this kind of silly F prime that you get by extending F along this composition. And the fact that this composition factors through T means that F prime has a T reduction, unlike F. And so there's this claim that since the punctured XR is an affine scheme, and your unipotent radical U is filtered by copies of the additive group, you can basically always reduce a B bundle over this punctured XR to a T bundle. You can ignore this U part. So I'm not really sure how all the formal details get written up. There is a link embedded in this slide, which goes to a Math Stack Exchange post, which is about the case where R is K, right? So just a punctured curve. But XR is not a curve. XR is a family of curves over spec R. So I'm just leery about that. Anyway, so let's assume F has a T reduction. So the nice thing, of course, is that you should think about T bundles as being very similar to line bundles, right? T torsors over X form a group stack. You can compose them, and if you think about what's going on at the level of line bundles or totally split vector bundles, what you're really doing is you're tensoring those associated bundles together. So what we'd like to say is that if you have two T torsors over XR, and they differ by co-character, so that is to say, the extension of structure group along some co-character of some GM torsor, then the associated G torsors you get from extending the structure group are isomorphic at tau locally. So this is a fancy way to say that we want to say that we can reduce the case of a trivial. We want to say that if we have a T torsor, any T torsor, well, it certainly differs from the trivial T torsor by some linear combination of co-characters. And then we want to say that the G torsor associated with it differs from the trivial G torsor just by some étale base change on spec R. So here we use the fact that G is simply a connected semisimple. I probably want the word semisimple here. You can assume that your co-character is a simple co-root, because in this case where G is simply connected, the simple co-roots generate the co-character lattice. And so you reduce the case where G is generated by the torus T and the image of Laszlo under the root homomorphism associated with this co-root. And so it's some Lie theory calculation that any such G, it has to be the product of SL2 or GL2 with some smaller torus. I'm not sure. Well, so here we're leaving the simply connected world, but we've already used it where it counted. So at this step, now we're working with a slightly more general kind of group G, but it's okay. We can completely solve this case. So the point is we're reducing to a linear situation. And here, this calculation goes back to Beauville Laszlo in a different paper, the paper called Conformal blocks and generalized data functions. So you can show that in general, any SLN bundle on a punctured curve trivializes after you remove at one point. And the statement is still true if you look at a family of SLN torsors parameterized by some spec R. And the way they prove this is by induction on the rank. Basically, if you take the associated vector bundle with trivial determinant, after you twist sufficiently high by the pole at the point you punctured at, then you can split your vector bundle, and then it splits totally by inductive hypothesis. The GLN case is similar, and that's how this proof concludes. So this paragraph is taken verbatim from Drinfeld Simpson. And what's on these two slides is really just repackaging a single page of their article. So last thing I want to mention is that I said that this uniformization map is formally smooth. And this is a one-page thing that is a bit easier to explain than all the crazy stuff that came before. So I'd like to mention that. So what does it mean to be formally smooth? It means that if you creep along infinitesimally up to first order in the base, then and you have a lift of your starting point to the top space, then you can extend the path you creep along. You can lift it up to the top space. So more formally, if you have a point of BunG over R, and you've lifted it to a point of GR globe over R, and you extend your original BunG points to some R prime points, you can, and R prime is some square zero extension of R. So it looks kind of like a, like this. Then you can lift your R prime point of BunG to an R prime point of GR globe. So if you unpack definitions, what you're trying to show is that if you have a G torsor E over X sub R, and you write E prime for its base change to X sub R prime, and you have a section, any section of the ladder bundle, it must come from a section of the smaller bundle. And here I mean sections over the puncture curve. So smoothness is a surjectivity statement. Smoothness is a lifting statement. And so how does that, how do we see that at a glance? Well, just by unraveling definitions. R prime has a spectrum which is a square zero extension of spec R. So this map here is a square zero extension, affine locally. And this map here is really just it's just a G bundle. It's a G torsor. So in particular, this right-hand thing is smooth. And so now stare at the diagram of four things where the arrows are this composition, and this vertical arrow, and this vertical arrow, and the identity map on the base. You have a map down here, you have a smooth thing over here, and you've got a square zero extension of the test space you're using. So by the definition of the smoothness of this map, you can lift your map downstairs up to some diagonal map this way that commutes with the upstairs map here. That's what it means for this right-hand map to be smooth. And this diagonal arrow, which you just filled in, also happens to be precisely the alpha which you wanted to lift from your, it's precisely the lifting that you wanted to get the surjectivity. So this is the last slide, but I wanted to make one more remark, which is that there is a generalization of a lot of these things where you take multiple punctures on the curve. So throughout my talk, I was working with one puncture. I believe that you still get these kinds of formally smooth, all these nice properties of uniformization, where you place this global affine Grassmannian with one puncture with the multi-leg so-called Valence and Drinfeld Grassmannian. And again, the map down to BunG is just for getting the the section away from the punctures. Okay, I think I'll stop there.
Woo! Oh, yeah!
Thank you.
I'm not quite sure how we thank the speaker, but that was it. All right, 10 out of 10. So any questions for Minh-Tâm?
I know that was brutal. I'm sorry.
No, it was so interesting to see that, and thank you so much because it is such a terse paper, Drinfeld. So I guess I just have maybe I don't know, it's a comment / question that in the case where R is K, this does assert that for simply connected G, semisimple G, any G torsor over the curve minus a point is trivial. So it's
Yeah.
a trivial statement because they're only, the only atoll covers of spec K are just spec K assuming it's algebraically closed.
That's right.
Actually easier to see than the full force of Beauville Laszlo over all the R, than of Drinfeld Simpson over all R, or, I mean, certainly it's a consequence, but it feels like, would it be about as difficult in the end? I mean, or.
So I would say it this way. I would say that there are these two theorems. This theorem, the existence of a B reduction. Remember, so we proved this part in 2 steps. The easy part is this part, which is the statement that if you have any G torsor over X, then you can find some B reduction. That is the easy part. The hard parts are, well, next you want to show that if you impose more conditions on G, then after puncturing a point, you can trivialize the G torsor over the punctured curve. So what I'm saying is that this is easy in the case where R is K.
Okay.
But this is, I don't know how to do. It's easy for SLN because for SLN you have this trick where you can twist vector bundles basically, and you can manipulate vector bundles in a much nicer way than arbitrary principal bundles or things that come from them.
Is there not a way of sort of using the Tanakian formalism then to describe sort of like twisting, where you twist by a co-character valued
that would be an interesting thing to write. I don't know if it's already been done.
Yeah, I mean fascinating. And then the Steinberg theorem that you cited, I take it, is this cohomological, this theorem, basically a Galois cohomology theorem about function fields, right? Trivial. It's sort of, So that's what means that's what gives us the fact that if you remove a finite number of points, something will be trivial. That is generically trivial over some risky open subset of the curve or something like that.
That's right. That's right.
But doesn't matter just one point. I mean, then like line bundles already show they have non-zero degree already show that you need that you might have to remove more than one point to risky trivialize.
Yeah, you might need more than one point a priori, and there's something special about simply connected things. So I guess
simple in the semi-simple stop there from a determinate sort of line bundle construction, right?
Yeah, you're not, line bundles are ruled out. GM torsors are ruled out. So in the way that Drinfeld and Simpson write it, they make it sound as though simple connectedness is only there to ensure that the characteristic of the base field does not divide the order of the fundamental group of G.
Okay, that makes sense.
But
and this is fantastic. There was one other question. Anyone else have any questions?
I was just going to ask. I was just curious if you going back to that insmoothness question, if you had like a reference for that or where you got that claim, because I just wasn't clear on it.
You know, I wrote this like at literally 4 a.m. this morning, so it probably was out of my ass.
I see. Okay, you might have meant formally smooth.
Joachim Heinloth, Uniformization of G bundles is probably where I remember it.
I see. Because I had kind of a different, I mean, I guess another way to think about this formal smoothness is like this map is, it's actually a torsor for like the space of maps from X cross into G.
Yeah.
Right, and that you can see is formally smooth using like a Kodaira-Spencer type calculation, right? Because it's whatever the relevant obstruction is like basically H1 of the affine curve.
So is that what Gates-Corey does in his contractibility of the spatial rational maps paper?
I think that's something much more complicated, right? Because he's considering this full moduli space of rational maps from the curve into the group where the domain is possibly varying. This is something much simpler because it's just maps from the curve with a fixed puncture.
Yeah,
Right.
I agree that Gates-Corey's result is much stronger, but I wonder, it's implied, right? The Kodaira-Spencer calculation you're doing is implied by stuff in his paper.
Oh, maybe, but again, that space of like the full space of rational maps is like much more complicated. Like it's not an N scheme, for example. So
Yeah.
I'm not sure. Yeah, like it's because if you allow the poles to vary, then you get something quite complicated. Like it looks like a quotient of an N scheme by an N schematic equivalence relation or something like that. So it's pretty nasty.
I see.
So this thing, like, for example, like if you take, if the group were GA, for example, which is not really allowed, but if it were GA, then it would just be it would just be like an infinite dimensional vector space. So it's kind of plausible actually that it's in smooth. I just don't know actually how to see it.
Yeah, so my point is that the formal smoothness is somehow very easy.
Yeah.
It's just this one page.
Right.
Speaking of which, does anyone know how to get diagonal arrows nicely into a beamer? Because you can use Tixie, but then there's this horrible thing where if you make an error in your Tixie, it throws up an error page in my LaTeX, which is a separate file from my original LaTeX document. And I always misclick and try to compile the error page.
Wait, do you know about this amazing website which allows you to just draw the Tixie CD diagram?
It doesn't work consistently for me.
Oh, I only just found out about it, so I haven't become such a strong user that it's stopped working correctly for me. But I think that was life changing. Yeah, no, I never am going to be drawing a programming commutative diagram by hand again. I guess I have one other small question. This locus of BunB, where it's sort of BunB to BunG is smooth, was sort of implicitly used in this argument. That's called the anisotropic locus, right, or something like this. Is that the correct thing? Because I remember Drinfeld emphasized that was like a very important aspect of the proof that you sort of look for a sufficiently unstable B bundle, and if it like becomes more unstable, it becomes more like the map to over BunG from BunB to BunG becomes more smooth, and so that's sort of implicitly being used. I mean, very much in what you wrote it out explicitly. I just was wondering if there was some sort of like broader context of that
I do not understand what is written in their paper.
Okay.
It completely flat out. I understand Larry's notes.
Okay.
I think this statement, Aaron, you're referring to is like if I look at the map from BunB to BunG, like BunB has a bunch of connected components indexed by co-characters, and it's the map is going to be smooth on components which are sort of sufficiently anti-dominant.
Okay. And is that called the anisotropic locus, or is that...
I've never heard it called that, but maybe it is.
Yeah, sorry, I may have picked that up incorrectly, but yes, sufficiently anti-dominant. Okay.
Basically, the same cohomological calculation that Minh-Tâm did.
Yeah, this was the one point that we managed to sort of extract from Professor Drinfeld regarding the insight into how the proof works. Is like he said, he didn't have much to say, but this one point. Brilliant. Any other questions for Minh-Tâm? All right. Well, thanks very much.
Great.
End the recording.